Starting back up here with number 18. Now again, this is going to be part 4 of module 1 of math from the test above. That's going to be test 3 from the College Board site, the 6 paper tests. So yeah, let's jump into it. This is where it's going to start to get fun. Some of the better problems are going to be in these last 2 pages. And yeah, let's see what number 18 has in store for us. So I see, it looks like it's going to be an equation problem. The product of 2 positive integers is 546. So already I'll say, okay, x times y is going to get me 546. So we should be pretty good at making equations now if you followed all my other tests. But they have to give us a second equation, right? If the first integer, we'll say x, is 11 greater than twice the second integer, so is. So x is equal to 11 greater than twice the other integer, 2y plus 11. Sounds right? What is the smaller of the 2 integers? Okay, so it looks like I could probably honestly just throw both these in Desmos, right? So let's get Desmos pulled up. We don't really have to solve for any of these system of equations on the SAT. So Desmos is right here. And I'll go ahead and just throw my 2 equations in. X times y. Oops, they don't like all caps. X times y is equal to 546. And I think we'll be looking for some sort of an intersection point here. 2y plus 11. And I want to zoom out, or rather 2 intersection points, right? So I see 39 and 14 for a positive x and a positive y. So 39 and 14. So it looks like down here, these are just going to be the negative numbers that make this function. Because again, in my first equation, we have positive times positive, or negative times negative to get a positive number. So they want the 2 positive integers, which is established. And let me just hide this real quick, which is established right here. So it's cool. I just jumped to the top right quadrant. And it looks like my x should be 39 and my y should be 14. And it's nice they specify they want the smaller of the 2 integers, so it should be b here, or 14. And just to double check, that is correct. Perfect. And number 19, it looks like probably another Desmos problem, so it's nice that we already have it pulled up. So Desmos again, anytime I see these, these 2 function problems like this, I just throw them both in Desmos. So my first function is going to be y is less than or equal to x plus 7. So it's going to be inequalities, which is a little bit tougher to read, but I think it should still be fine, especially if they give us multiple choice answers. So they do. So I'm going to shift this down so you can see. They want to know, is a solution to the given system of equations. So on my Desmos, I will kind of try to move around. I'm trying to see both at the same time. So we shall shift around for negative 14. Does not look like it's going to fit. Negative 14 in my x, negative 14 in my y. Does not look like it's going to fit. Positive 14 does look like it's going to fit. We always want the double shaded area, right? So positive 14 for my x, that looks like it's going to be D, correct? Let's just double check that's true. And D for 19 is going to work. So again, you're always just looking for the point that meets both the purple and the green. And on Desmos, that's going to be kind of like your multicolored area. So not too bad. Another Desmos problem. And I'll scroll down a little bit further here for number 20. So what to do here? I see a couple x's. I see a couple square roots. So the first thing, this inclination we want to build for 20 is I want to square everything. I can't really do any math when both my x's are trapped under square roots. So if I square both sides here, I should get x minus 2 squared is equal to 3x plus 34. And it's actually funny. I just thought, well, this is going to be a quadratic. Instead of trying to solve for x by hand, I could just throw it back in Desmos, right? So let's go ahead and pull Desmos up again. And honestly, I could leave it as it was. I already solved for it a little bit. You should be able to use the square root function down on your keyboard. So I'll try to do it here. So down at the bottom, there's a keyboard and I see, no, that didn't work. Let's try that again. So I think I have to type in the number first. So let's try this. Let's try x minus 2 and then to the second. Technically, I could just raise it to the 1/2 for my square root, but I want to make sure they have the button here, and they do. It's going to be right there. Okay, so let's try to put that before this, kind of like that. Oh, so they want me to type the whole thing underneath it. That's fine. So square root first. Good to practice on Desmos. And then we put x minus 2 to the second. And that way, this is just going to save you the most amount of time because you don't have to solve for anything. And that's going to be equal to, type square root first, then type 3x plus 34. And then I should find my two solutions here. I'm going to zoom in for you here. And it looks like my two solutions are going to be 10 and -3, it looks like. So let's type these both up. 10 and -3, and I'll remove Desmos. And they want what is the smallest solution to the given system or given equation. And it looks like it should be -3 for 20, and that is going to be correct again. So practically 3 Desmos problems in a row. You see how prevalent these are going to be, right? You want to try to be an expert on Desmos. Use it as much as you can. We got a couple more good ones here. Oh, this is a really good one. Number 21, let's see how to solve this one. So we have a regular price of a shirt at the store is $11.70, and the sale price of the shirt is 80% less than the regular price. Okay, so if it's on sale, we want to think, as opposed to doing, you know, the 80% and then subtract it from $11.70, just think, oh, it's going to be 20% of its original value. So I would just do 20% times $11.70, or think, you know, 0.2 instead of 20%, right? So if I do 0.2 times $11.70, the sale price is going to be very cheap. That's going to be a $2.34 shirt, okay? And then I think they're going to give us another step here. The sale price, so that's this. This is where it's really important to label your units. This is my sale price. This sale price is 30% greater than their cost. So that makes sense. In order to make profit, they have to charge more than what they're paying. So if that's 30% more, try to think of C as the cost. So the C, the cost, is going to be rather less than this 234. So whatever division, whatever multiplication we end up with, we should get a number less than 234. So how do we do that, right? I could try to say, okay, if this 234 is 30% more, I could say 234 is equal to, and this is where it's really important to practice our percentages. Try to think of 1 as there's no change, right? If there's a decrease, I go below 1. If there's an increase, I go above 1. So if I'm starting at 1 and this 234 is 30% more, then technically this would be equal to 1.3 times our cost, right? So 30% more times our cost is going to get this sale price, which is 234. So just to make sure we get a good number here, if I divide both sides by 1.3, let's see what we get to make sure we get that number. So 2.34 divided by 1.3, and we get 1.8. So that would be the cost of the shirt is 1.8, and then contextually we make sure that makes sense. 30% more than the cost of our shirt should be 234. So just in case, I do 1.3 times 1.8, and I get 234. So you see how these percentage problems a lot are just context based. Try to establish that 1 as being neutral, above if it's an increase, below if it's a decrease. We always want to start at our original cost, right? So we're starting at C, and we would need to increase it by 30% to get to 234, as opposed to decreasing from 234, if that makes sense. So always try to start at your original. Very good problem. You can try that one again. And then number 22, another cool one here. So we have a sample of oak that has a density of 807 kilograms per cubic meter. So 1 meter cubed. Okay. And they tell us that's density, right? So that's going to be D is equal to kilograms per meter. The sample is in the shape of a cube where the edge length has a length of 0.9 meters. So already, you know, the units brain, if you've practiced a lot of these unit problems, I don't care about 0.9 meters. I maybe care about meters cubed. So already I'm thinking, what if I did 0.9 times 0.9 times 0.9? I would get 0.729 meters to the third power. And I'll shift that over a little bit for you. And the reason I did that is I always want to keep my units consistent, right? is this going to be a problem where I do like a third root of kilograms and meters cubed? And that's just not going to be a thing. I don't see cubed root of kilometers or kilograms anywhere. But we already have established kilograms per meters cubed. So they're giving me meters. I need to make sure to cube it to keep it consistent with my problem. Now, I imagine they're going to ask something about kilograms, right? Because I have this kind of blank space here. So kind of mastering this test is all about anticipating these questions. They say to the nearest whole number, what is the mass of this sample? So it's perfect. We've already established our meters cubed. Now we need to figure out what this change is going to be, right? So it looks like my meters cubed has decreased. So my top has probably also decreased. Specifically, I could find how has this changed percentage-wise, right? And it should be the same change. I could also probably cross-multiply, but let's see. So I could do technically 1 minus 0.729. And it seems like this has decreased by 0.271 or a percentage of 21%, right? We've decreased by 27%. So if I go up above and I type, okay, if we're decreasing by 27%, technically I should be left with, remember, we don't like the change, we like what's left. I think that's going to be 73%, right? We should be left with 73% because we've lost 27%. And I just do 73% times 807. And I get very, very close to this answer. I get 589. It's 588 because we rounded a little bit. So we get something close to 588 here. And the reason is this sample, this material is not changing. There's nothing in the problem that says this 807 per meter cubed that the density is changing. We've decreased in volume, so we should decrease in kilograms, and it should be by an equal percentage. So not too bad. Again, great problems. Wrapping up with number 23 here, I see f of x is equal to 201% of x. So to try to think of some numbers that could work there, if x was 10, 100% of 10 would be 10, right? So 201%, right? 200% would get us 20, but then that extra 1% should get us an extra 0.1, right? So 201% of x would be 20.1. And now we want to establish, is this going to be like an exponential relationship or a linear relationship? So we know it's increasing. So I don't know why A and B are options. It's not going to be those. We know it's an increasing relationship. Is it exponential or is it linear? And this is where we really want to look for words that establish an exponential relationship. So if it was like increasing by a percentage of its current amount, that's a really good one to sneak in exponential. Because if its current amount was like 10, and it was each year it increases by 100% of its current amount, next year would be 20. And it's not going to increase by another 10, it's going to increase by its current amount, 40, 80. So once you see that this is not a constant changing value, plus 10, plus 20, plus 40. Do you see how that's not constant? If it was linear, it would be plus 10, plus 10, plus 10. So real quick, just to test this one, if I made an x, so what did we try? X is 10. Let's do x 10, 20, and 30. And 201% of that is just going to be, we already did this one. This is going to be 20.1. 200% of 20 is going to be 40.2. And 200% of 30 is just going to be 60.3. And I look at my change in my numbers, and it looks like it's going to be increasing by 20.1, 20.1. This is going to be linear because there's not an increase on each subsequent amount. It is just a constant increase from the start, right? So always look for that pattern. If it's increasing more and more and more, that's exponential. If it's increasing by a constant amount, that's linear. So awesome practice problem here, and we'll be jumping into these really good problems on the next one. This is going to be part 5 here.